as well. So
Okay.
thank you for your patience. Chris is having some technical difficulties, so he's going to use the phone for his audio. So this is one of our series of webinars from the SIGHPC Education chapter. And Chris is a professor of physics at The Ohio State University, and he's going to talk to us today about his STEM coding project. So Chris, I will turn it over to you. And I'm going to mute because my allergies kicked in today and I don't want to interrupt you with a sneezing fit. So, but I'll be watching the chat and I'll let you know if there are questions as we go along.
Okay. Thanks, Steve. And about how long should we go?
About 40 minutes, maybe, then time for questions.
Okay. Great. So yeah, I have a little bit of a cold too, so my voice sounds a little bit like a frog. So I apologize for that. So I like to show this slide first, before I get into any of the details and collaborations and things like that, because I think it's something like this is what I think is appropriate kind of in high school level courses to integrate coding, but in a scientifically motivated way. And so you can see from looking at this activity, there's some real heavy lifting in terms of modifying the code that the student has to do to get this to work. But once it does work, then you get to see the velocity vectors, you get to see the acceleration vector, the force vector, things like that. And then you can change the parameters of it and see how easy or hard it is to survive in the asteroid field. Based, if your ship is heavier, then it's harder to accelerate. It might be harder to survive for a longer time. And so you're doing something that's very much coding motivated, but you end up with something that connects rather closely with sort of the concepts that teachers are supposed to be teaching at this level. And so this kind of in a nutshell explains kind of our approach. Sometimes we call this a game-centered approach to incorporating coding into STEM. And I gotta close this thing, so that's my phone. All right. So I have a bunch of collaborators on this project. I don't know if Rochelle Feeling-Smith is tuned in or not, but I was just talking to her on the phone this morning. She and I work very closely on this project together. And there's other people at Ohio State like Chris Porter and Kathy Harper. We get their advice and some input from them from time to time. We're very grateful for that. But we'd like to collaborate with more people, and I'm happy to talk more about that. We also are very fortunate to have a bunch of students that help us out on this project. Now, I want to talk generally about incorporating coding into intro STEM, and when I say intro STEM, I mean kind of high school STEM, high school physics, chemistry, math, high school physical science, but also sort of freshman 101 level college courses, physics, chemistry, math there too. Physics is important because if you look at the participation there, most high schools don't have a computer science class. And so all the work that code.org is doing, which has been great to increase the number of students taking computer science, is fantastic, but it's still true that most high schools don't have computer science. However, there are a good number of high schools that have physics. And one of the things that I'm aware of in this work, and I'll talk a little bit about that later, is that physics is one of the least diverse academic disciplines, and so there's just not a whole lot of women and underrepresented groups that are involved in it. And coding provides a different way to experience physics, and so maybe one of the reasons why those statistics tend to be the case is because in taking a physics course, you have a particular experience, and only particular kinds of students can succeed in that environment. And so coding is kind of a way of reinventing the curriculum. And I'm mostly going to be talking about physics today, but you can apply this for chemistry. And if somebody wants to jump in and say, what would you do for chemistry? I can probably go on for like a half hour of what we would do in chemistry, what other people have done. We can also talk about math as well. But coding is a great opportunity to kind of rethink these courses. Now, I'm going to show you something from our Hour of Code submission, and the link to it is there. And about a year and a half ago, I went to the Hour of Code, and I searched on, if you look on the left here, it says science. If you click science, and then you click typing languages, so in other words, you're not selecting on the block-based languages like Scratch or Blockly, things like that. Instead, you want to do typing languages. There's only 3 things that come up. And when I saw this, I was shocked, and I realized I had to do something about it and to create our own activity. And in another slide, I'll show you our physics of video games activity. But I think this slide shows that the code.org initiatives, I think that they're very focused on computer science and creating a pipeline for computer science, because they're very focused on creating a pipeline of software engineers that can work at Amazon and Microsoft and Google and all that stuff. They're not as focused on incorporating coding into traditional STEM disciplines, and which is sad to me as a computational physicist. So one of the things that I should say before we get much further is that my background is in computational physics and high performance computing. I've used all kinds of different supercomputers in my research. I've done cosmological n-body simulations from a PhD thesis. I've done particle and cell plasma simulations with ultra-intense lasers in it. That's one of my main research thrusts. And so I come from that background. And what happens to me year after year is that there's undergrads that show up in my office, and they say, hey, I want to do a research project with you. And I say, well, can you program? And they say, no, I can't program. I've never done that before. And, and you look at these kids' transcripts, and they have like a 4.0 out of high school, and nobody asked them to program. And so in a certain sense, this project, the STEMcoding project, it's almost like trying to fix that. I mean, it's the kind of resources that I wish I would have had when I was in high school, thinking about science, thinking about coding, things like that. There really just wasn't much out there at the time, and we really need to fix this. It's actually kind of a shame that the way that this has all happened is that code.org and various groups are investing heavily in sort of elementary school and middle school coding activities. The thing that would have made more sense in my mind is to start at the high school level and sort of go downwards. And so at the high school level, they're almost playing catch up, because there's all these kids that are learning Scratch in middle school now, but there isn't necessarily a curriculum for them to just sort of move into in the subjects of physics and chemistry and advanced high school math and things like that. End of rant. Now, what I'm glad to say is that this is changing. And so now if you go to hourofcode.com and you search on science activities, you'll see quite a few more things there, one of which is our physics of video games activity. Can people hear me okay? Does this sound okay? I'm looking at you, Steve.
Yeah, it sounds fine.
Okay, thank you. So if you go to hourofcode.com/learn, and then what you have to do is you have to click on comfortable level activities. So we submitted it to the Hour of Code, and we said, this is for absolute beginner 9th graders. And they said, no, it's for experienced 6th graders. And we were like, okay, fine, whatever. So you have to click on the comfortable level, but you'll find this. And what we're trying to do is we're trying to use the video games that kids play to get them to think about what the computer is doing in the background. And so we start this video out with me kind of bad-mouthing Mario Kart, and I'm complaining about Mario Kart and how the physics is not very good, and how you go from air into water and you don't slow down, and you bump into things and you do these perfect 360-degree turns. You're sliding through these turns, but you're still in control of the thing. And there's numerous ways in which the physics of this game is not very accurate. But then there's other games that are better than that. And so I show them some of the more realistic games, like BeamNG Drive and things like that. And I say, do you see how this game looks differently than the Mario Kart game? And do you see how the physics are much more accurate than that? And again, I'm emphasizing the physics, but any kind of if you think about any kind of simulation that people are doing, I mean, that it's going to be based on those kinds of similar concepts. So part of what I'm doing is to say, well, for the kids that end up in my office wanting to do a research project, but for all the other kids, there's a lot of engineers out there that now on a day-to-day basis will use a sophisticated computer simulation to model, the stress and strain on a bridge, to model the heat flow through an engine. I mean, I don't even have to tell you guys. You guys probably give me a lecture about it. And so we need to have something at the high school level that isn't just like, here's what an if statement is, that isn't like, here's object-oriented programming. Like, object-oriented programming is great, but how do you apply it to science concepts so these kids, that when they eventually become engineers, they have some amount of intuition for what this computer program is doing. My mom, actually, to tell a personal story, she's engaged to a NASA engineer, and he does these structural analyses of these rockets, and he says that there's these kids that come from undergrad with an undergrad degree in engineering, and they put everything in the computer and they press a button and the computer says everything's fine, but they don't know how to test this engineering program to see if all the rattling that happens is correct. They don't know the test cases. They don't know the limitations there. And so we really need to reinvigorate the high school and early college curriculum, preparing kids to putting them on a trajectory where they can sort of get to that level of maturity. And the more we do earlier, the further we can get in undergrad level before they graduate. So this is, so I talk a bit about that, and how sometimes it's more fun to have realistic video games. And so that this is the setup, the Mario Kart and the realistic games. This is the setup for the next part, which is what I call Move the Blob. Now, Move the Blob is based on a popular game called Agar.io, AGAR.io, and my kids were the ones that introduced me to this. And you're a little circle, and you're moving around at constant speed, but you can change direction based on where the mouse is. And so it's a very simple game, and it should be possible to kind of mimic that in a coding environment. And as kind of our first video game. It's also sometimes called Nebulous, if you've heard of that, but it's a very popular game. I gave a talk in front of 150 high school math students, and about half of them recognized the name of it. So this is kind of the next screen that you get to. So this is the code, and I'm going to focus on the code in a second. But basically, you run the program. You kind of click here to run the program. For idiosyncratic reasons, you do have to click on the screen, but then you can move this object to the right by pressing the right arrow. But if you press the other arrows, nothing happens, which is not very fun. And so if you kind of want to stare at this code, so this is the entire code. It's about 40 lines of code. And so you have some initial variables here, and then this draw function is going to run over and over again. And we're going to update the location, set the velocity equals 0. We're going to check if the arrow keys are pressed, and we're going to display some stuff. I'm going to focus on just this draw function here for a second. And so, you notice that when you press the left arrow, nothing happens. Well, that's because when it presses the left arrow, it just does nothing. It says do nothing. And so that invites the student to kind of replace that with something, and maybe they'll guess Vx equals -10. Maybe they'll accidentally guess Vx equals +10, and they'll kind of have to troubleshoot until they get the thing to move left and right. And then likewise with the up arrow, they should put Vy equals 10 there, which they can probably guess, because if you want to move up, that's the y direction. But that doesn't actually allow the thing to move up until you go up here and you say, oh, well, we forgot to update the y location. So you have to have y plus equals Vy times dt. And so they can almost kind of, it's almost self-guided the way that you can kind of go through this code and kind of get it to go from something that's not very interesting to something that's a little bit more interesting. Now, the next activity after that, and this is still within our code activity, this is sort of the last part of our code activity, is called Accelerate the Blob. And the idea there is that a code where you set the velocity of this little blob, the velocity is either constant this way or 0. That's not very realistic, because that's not what happens in real life. In real life, things are either going at a certain velocity or well, in real life, things have to accelerate up to a particular velocity. They don't just jump to that velocity instantaneously. And so a much more accurate program would be if you could have the arrow keys control the acceleration, and then that would change the velocity every time step. And so, so it's a similar kind of thing where you start out with initially this blob can only accelerate to the right. You've got to modify it until it can go in the other directions. And when you're done, you get this kind of interesting looking thing that you can kind of play around with. And you can leave behind, you know, a trail of little dots, which can connect to like the learning standards, the NGSS standards, things like that for velocity and motion. The further apart those dots are, the faster it's going, and things like that. So that, but the important thing is that this is a much more realistic game than what we started with. And we could even, you know, and so it kind of invites the student to think about how do we make this more and more and more and more and more realistic. And if we were to do this in 3D, we certainly could, but the code is going to look quite similar to that. So what's the purpose in doing it in 3D, really? You know, that's kind of my attitude. And so we submitted that. We got that hour of code activity posted to the National Hour Code in November 2017. And for those of you who are involved in computer science education, both our hour of code activity was posted in November 2017, as well as a whole bunch of other ones. I would say we're still the first and most physics-focused hour of code activity that's there. But if you checked the hour of code activity a year ago, you might want to check it again because they seem to have almost twice as many activities there than they did, which is to their credit, which is fantastic. So after we finished the hour of code activity, we kept on recording more videos for the YouTube channel. And I'll talk a little bit later about the research that we're doing. But we're very excited to have this STEMcoding YouTube channel, and the link is here. Now, the thing about our YouTube channel is that if you look closely, it's not necessarily obvious, but if you look closely, we have a high percentage of underrepresented groups in STEM that we feature on this channel, which is not an accident. I mean, we kind of actively, we have some grant funds from the American Institute of Physics to do this, and we actively recruit good students from different backgrounds to appear in those videos because we need to create a resource for students so that the kids out there can see someone who looks like them doing STEM, having fun, learning to code and things like that. The unfortunate reality is that if you look on YouTube, almost every single STEM-focused YouTube channel that you can find, and there are exceptions to this, and there's fantastic channels, there are exceptions to this, but most of the STEM content, especially in physics, is just white male dominated. And I don't know what it is. I don't know why there's so many, but you know, this really needs to start to change, and we're trying to do the best we can with our YouTube channel. So I strongly would appreciate it if you could share this with the teachers in your networks and students and things like that, because we're going to keep on recording. We're going to keep on recording these coding tutorial videos as we go. And in a lot of ways, this is a resource for the teachers as much as it is for the students, because there's a lot of teachers out there that are very unfamiliar with coding. And unless you show them exactly how to do it, they might not do it.
Chris, one question came up in the chat. This is all free, is that correct?
Oh, yeah, absolutely. 100% free.
Yeah.
Yep. So we have, you know, over a dozen exercises, probably less than half of them we've had time to make videos out of. And so I'm kind of highlighting two here. So this is planetoids with the spring on the top right. And then on the bottom, we have this charged particle getting accelerated into a magnetic field. The idea that particles go in a circle when they go into a magnetic field, if you want me to prove that on a chalkboard, it would take up an entire room of coupled differential equations. If you want me to do it in a computer program, I can do it in like 2 lines, and it just iterates it and it just goes. So it's part of the beauty of this, and it's part of how you can use this in sort of an algebra-based course because you're letting the computer do the calculus for you. So you have a whole bunch of activities here, and I want to highlight a few things about these activities. All these activities have animations, and I've taken all the computational physics classes. I know a lot of you guys out there have taken, graduate level computational stuff. And once you get to a certain point, there tends not to be very many animations of things, at least in computational physics. And so, there's at least animations with this. And a lot of people look at my stuff and they say that it's similar to like the FET group from Colorado, which does fun things. So they all have some sort of animation in it. Not all of them have interactivity, but many of them do. And this, again, is something where, in my computational physics background, I've taken the graduate level computational physics. I've taught graduate level computational physics. And once you get to a certain point, you do not interact with that program as it's running. That wouldn't make any sense at all. But in high school or early college course, you want the students to interact with the program because that's how they build their intuition about these concepts. And that's true for physics. I can imagine that being true for chemistry and math as well. And there's some connections to chemistry and math here. So for example, Pong and Bonk.io. Pong is very, very similar to the kinetic theory of gases because you just have these elastic collisions everywhere. So Pong, as stupid of a game as it is this beautiful example of how you can talk about elastic collisions. It's one of our more popular things. Bonk.io is a game that my kids told me about, and all it is kind of a Pong game that you've add gravity to it. And so it's a perfect example of, it's very closely related to that. It's a fun game. And, and for chemistry stuff, it helps to illustrate that, objects at the bottom of a box are going to be moving more quickly than they are at the top of the box. And so again, you're connecting with those concepts. Now, one funny thing that I like to point out, I'm just checking the time here. One funny thing I like to point out is that if you look at what the other coding initiatives do, so let's say there's some other coding initiative that's going to make a Pong activity, right? Because Pong is a popular game. That would be a fun thing to make an activity out of. Well, so Swift made a Pong coding activity as part of their Swift playgrounds, and which is fine, which they want to teach kids how to work with the code and things like that. The funny thing is that if you look at that Pong game and you look at all the different programming tasks with that Pong game, they want you to change the color of the ball. They want you to change the location of the blocks that it's bouncing off of. They want you to change the sound effects when the ball bounces off of things. But you want to know what they don't do in that Pong game? They never, there is nowhere in that code that shows of what happens when the ball bounces off of something. What happens to the ball's velocity when it bounces off of something. If you look at my Pong game, the only thing that I show is what happens to the velocity of that object when it bounces off of a surface. That's it. I don't let the students change the color of it. I don't let the students change the appearance of it. The only thing that they are there to do is to make sure that that ball is going to bounce on the surfaces where it is supposed to bounce. And if it doesn't do that, they need to keep on working on the code. So that kind of helps to illustrate the difference between the STEM coding approach and the different, which is really trying to help students to get some sense about coding as it relates to science. That's the difference between our approach and an approach that, Apple doesn't care if programmers know how the ball bounces against the thing. They couldn't care less. They want to know if you can handle object-oriented programming. They want to know if you can modify this if statement and change the sound effects. They don't care if you know how things bounce. And so we really need to be absolutely clear that we can't allow the moneyed interests to just sort of have their way with the way that coding is going to be implemented into K-12. We really need to step in and do that. Now, an important part of that is validation. And I know you guys are out there, you're like me, you're HPC people, and it's all about verification and validation. Probably I should say verification here. I know there's probably somebody out there who's going to criticize me for saying verification instead of validation, but many of these activities, there are solutions for what is supposed to happen. So if you take the classic lunar lander game where you're trying to land on the moon, if you have that little ship and you just sort of let it fall to the moon, there's a certain number of seconds that ship will have. If you think about the Apollo lander, there's a certain number of seconds that it's going to have, and what speed is it going to have when it hits the ground, things like that. there's a certain amount of seconds that you can calculate. If you don't fire the thrusters at all, how long it would take until it crashed. And so what you can do is you can test that code. You can say, okay, well, we put gravity into this code. Does our expectation for the free fall time of this thing match up with the actual simulation? And usually it does within, a few percent. And it doesn't have to match up exactly because the computer is breaking this up into little tiny pieces. And so you don't necessarily expect it to match up perfectly. And that can be part of the discussion of like, well, it's, this doesn't match perfectly. How can we do it better? There's some amount of error that's being introduced here. And so all of the highlighted activities here have some sort of validation to them. And not all of them have validation. I feel like with like the Asteroids game where you're kind of flying around, I can't think of a real validation activity for that. But for other ones like Angry Birds, you got to make sure that that thing follows the trajectory it's supposed to follow. And the fun thing is, there's this sort of 1/2 AT squared trajectory that it's supposed to have. And in the code, you never put in the 1/2 AT squared, but it just sort of naturally does that if you do it right. And so it's this kind of way of double checking your work in your code. And it's an important habit to get students into as early as high school, in my opinion. And we have some videos for these things. As I said, we have a lot of work to do to record more videos. I'm happy we have as many as we do here. Excuse me. Assessment. So this is something that a lot of people think about. What is really the goal here? Like, what are we really trying to do? And because our assessment goals really have to line up with that. And so one of the most important things is this even at the appropriate difficulty? Are we totally overwhelming the students based on their math level, things like that? Another thing is just, are they having fun? Are they enjoying themselves? Not everything that students do in a science class is fun. An important topic is computational thinking, which I was thinking a lot about earlier this morning, which I can talk about if you're curious. And then the last one is kind of conceptual knowledge, and that's the one that I think about the most. And I'm curious if students can learn conceptual knowledge, perhaps even a little bit better from doing a coding activity. Is there some additional benefit in learning the concepts you can get from coding? And my personal experience as an HPC person is that, I'm trying to learn some new topic about physics or some area of physics that I'm not familiar with. If somebody gives me a code for how that happens, I can often look through the code and kind of figure out like, oh, that's all that it is. That one thing I didn't understand, all it is it's for loop over this thing. Okay, that's fine. And so for me personally, that's a lot of how I learn physics is from looking at the code. Now that isn't necessarily true of high school students, but there could be some kind of additional benefit to their understanding of, fundamental physics and applying it from doing a coding activity. And the kind of activities that we're doing, kind of checking the code, validating it, solving bugs and things like that, can that potentially increase their conceptual knowledge? So in terms of assessing that, here's an example of what we do. And so one of these three trajectories is correct. I'm not sure how rude of a speaker I should be to make you guys try to choose which one is correct. But I'll go ahead and tell you that the one in the middle is correct. The one on the side, the ones on the sides are wrong. And so the idea is that the one on the right here, you can see the object is accelerating in an area where it shouldn't be accelerating. So there's a magnetic field. The one on the left kind of has this kink in its trajectory, which is not what would happen in real life. With the one in the middle, just kind of makes a circle and comes back up. So one would hope that students would be able to get this answer correct after doing a kind of a coding activity that looks not so different from this. So that's one example of what we're doing. And maybe we're making a lot of assumptions there. That's fine. But we feel like somebody should be trying to do this work. Another animate. This is an assessment somebody else made of what happens when a rocket fires its thrusters, which is overall fairly similar to our Asteroids game. And so we can ask them which one of these trajectories is the correct trajectory. And I believe the answer is E. So when I tried this in my freshman physics classes at Ohio State over 4 semesters, so it adds up to 83 students, a lot of them didn't have very much programming experience. A lot of students that fell into the some experience category were actually taking C++ that semester. So I don't know exactly how much experience they had, but not a ton of experience before. And this is just the Asteroids game. Most of the students found it to be relatively straightforward. Only one of them found it to be extremely difficult, which was GAT, which I was glad to see. A lot of the students found it to be enjoyable or fun. That was good. And that's kind of the data that we were able to share at this point. We have more data than that, but that's what I'm sharing at this point. I think I'm almost done here, but one of the ways that we do this is that we have a learning management system for using these coding activities. And these coding activities are written in Java, and that's probably something people are curious about. And so on the left here, so this is what the teacher view looks like. And the problem I had with doing these things for the first 2 years is that the students would submit me all these codes, and I'd have to download them, I have to make a little folder on my laptop, I have to run them, and this would be kind of a tedious step, and I have to, give them a comment, and half the time they'd still need to make these revisions. But with this website that OSU created for me, the students can submit their codes, I can click a button, I can see their code, I can run their code, which is what you see on the right here, and then I can grade or comment on the submission. I can see the student comments there. So this dramatically speeds up the process of just having lots of coding in an intro class. Probably one of the main reasons why we don't do coding in intro classes is because, at OSU we have classes of like 500 or 1,000 in some of these intro classes, and it would be almost impossible to do it. But this at least provides a tool that you can get closer to that point. And we're planning on improving it. I have some summer training for high school teachers, especially physics, but eventually we might open this to other physics and physical science, but eventually we might open this to other disciplines as well. It's all online, and so it's just sort of online meetings, and we're using this same learning management system so that the teachers are the students in the summer training until they finish with it. Then I can give them the teacher. And now in terms of help, so I'm going to open up for questions in a second. But if you have a camp, please feel free to try out our stuff. If you have a YouTube channel, please feel free to add us as like a featured channel on the right. You can actually, it's pretty easy to do that. A featured channel or similar channels. YouTube decides what are the related channels, but you can choose what are the featured channels. And then please share our stuff with the teachers in your area. And then lastly, I was going to put another bullet point here is, if you want to collaborate with us in terms of like a NSF broader impacts, something like that, or if you have students that you think would be interested in recording videos for us, there's no law that says that we can't have some student somewhere find a green screen and work with us to record another video and we post it to the YouTube site. We don't get any money from the YouTube site. We don't get any ad revenue. There's really no financial benefit that we get from that. So if somebody wants to contribute videos or partner with us, or even on the research parts of the project, we're more than interested to participate with that. So I think that's about all we have. We have some great sponsors we're happy to talk about. And that's kind of my contact there. So Steve, do you want to do some questions? I can look at the chat thing.
Sure, I can look at that. But just for everyone's, so we're recording this, so if you didn't catch any of the links and that kind of thing, this will be posted on the SIGHPC Education site under the past events, and we'll have this uploaded to YouTube probably by the weekend, this weekend. So you can go back and review this and see all the links. So if there are questions, you can either unmute and ask them verbally, or you can write something in the chat window. So are there questions for Chris at this stage?
Yeah, feel free to chime in. I'm looking at what's on the chat room. Feel free to chime in.
Hi, this is Juana Moreno. Do you hear me?
Yes, go ahead, Juana.
Okay, I'm at the Louisiana State University. Great talk. I'm participating on a program funded by Louisiana Department of Education to train teachers to introduce computer science and computational thinking in high schools. This summer, we have to train 7 teachers, I believe. We were planning to use P5 and Python for a 10th grade course. So, I mean, your simulations, I think, are great too for the Pi5 component.
Oh, thank you.
So, yes,
There's another group called sciencesims.org or sciencesims.com, and so there's a physics professor in New York that's also using p5.js. So one thing I didn't talk about very much in the talk is that you can use JavaScript, but typically people use JavaScript in some sort of library. And so we use the p5.js library, which was developed by the Processing Foundation.
yeah.
It's also something that the Coding Train YouTube channel uses a lot. And it's a very well documented language. It just works great, and I've never had any problems with it.
Yeah, I mean, we knew about that, but mostly because we are also collaborating with people in digital media that they use P5 all the time, but what they are doing is not science motivated. It's mostly towards digital media. However, the curriculum we are trying to put together is a pre-engineering curriculum, so those were not very appropriate. So it's great. I heard your talk because it gives me very good ideas.
So there are a couple things in the chat window. One asks, are the activities written as lesson plans for teachers to use?
Yes. So last summer I hired a high school physics teacher, one of the best physics teachers in the state, and he wrote lesson plans for almost all of our activities.
Okay.
And so those lesson plans and those solutions are available. So if you want to send me an email, I can send that.
Okay, this is from Philip Eaglin. He says also he's a code.org facilitator and can see the need for this at an elementary school level. So Philip, just send a note to Chris and he can point you to the materials.
So one of the interesting things is that there is a group out of Germany who made a block-based version of p5.js. So the lady I was just talking to might be interested in this. And so it looks like Scratch, but what it really is p5.js. And supposedly there's a way of hitting a button to export it to p5.js. So it might be a good way of transitioning from Scratch into a typed language.
Okay, are there other questions for Chris?
Can I say one more thing?
Go ahead.
In New York City, there is a creative coding with p5.js curriculum that I've not had a chance to see, but there's people in the public schools that are doing this. And so if people are looking for more p5.js things to do for various grades, for computer science, I think there's more material out there that exists, but I don't necessarily know where to point people to it other than to just go hunting for New York City computer science teachers.
Okay. One question that came in, what about providing lessons using Jupyter notebooks?
I have a few things to say about Jupyter notebooks. One is that they're not a couple of things. So I don't want the STEMcoding project to be tied to a particular language. And so my favorite language is JavaScript with p5.js. I think it looks a lot like C or C++, which are languages that people use in research, that I use in research all the time. But I know there's a lot of people out there that use Python, things like that, and I'm familiar with Python. I've used it in my research. I know all about it. In my opinion, Jupyter notebooks are difficult to set up. I went to a computational physics education workshop in Cleveland in which it took them 20 minutes to set it up. A. B, Jupyter notebooks do not give you the same kind of grid of student submissions to grade. I don't think it really has like a utility that allows people to grade. So my understanding was that people often use Jupyter notebooks for the kids to develop their codes, and then they submit it maybe to like a Dropbox or something like that. And then you go to the Dropbox and you see all those student submissions. So what I have instead is our learning management system. Our learning management system, you know, the student submits it, and then I can just see the code. I can run the code. I can comment on the code. I don't have to deal with Dropbox. I don't have to set that all up. I don't have to download all these folders and things like that. I mean, is the question about Jupyter Notebooks because they like Python so much, or is it because they like some other language that Jupyter?
I have to refer to the person asking the question. So, Camille, can you add more to your note or say something verbally?
Yeah, I was just wondering, not because Python is so widely used in many beginning STEM courses is one reason, but secondly, because it's easier to integrate both the applications you're creating along with other materials for the class. So it's sort of a little bit complete for sharing and for reusing.
Sure. So if you look at this slide here, you see where it says functions.js.
It's real hard. Yeah.
Yes.
It's a little hard to read, but so that functions.js file is where I define a whole bunch of functions that I do not want the student to see. And I don't want the student to see them because I don't want to overwhelm them, and I don't think that they're, you know, for the goal of the activity, which is to focus on the science of what's going on, to focus on the velocities and accelerations and things like that. I don't need them to see where I defined this arrow to be red. I don't need them to see where I defined the width of this arrow to be 7. You know, they don't need to see that. And so if they don't need to see that, I'm going to hide that from them, because otherwise that's what's called a distractor. Now, in Jupyter Notebooks and in glowscript.org, and I know this is GlowScript, and I'm pretty sure this is true of Jupyter. You can correct me on it. But in GlowScript, you cannot hide code from a student. There is only one tab. You cannot have another tab in which you can hide the definition of some function. And I point this out to people, and they just said, oh, well, you should still use Python. I'm just like, are you nuts? Like, if you look at the Asteroids game for Visual Python, it is 150 lines of code, all of which the student sees. My Asteroids game is 50 lines of code. And I genuinely don't understand why people wouldn't want to hide more code from the students, because you're always hiding code from the students. This browser has millions of lines of code that you don't see. So that's part of my response. The other response is that Python, in my opinion, doesn't have very good keyboard commands. So if you want to have a game, and so for example, if you take our move the blob thing, I tried to create it in Python at one point. And an important learning objective in that activity is being able to press the up arrow and the right arrow at the same time so the thing moves diagonally. Because that way you have a positive velocity component to the right and a positive velocity component up. That causes the thing to move diagonal, which is a very important physics concept. You can't do it in Python, or at least you can't do it without knowing a lot more about Python than I do. Because in Python, you can only press one key at a time. Because it was never designed to do games like this. And so that greatly limits what you can do with Python if your goal is to use Python to show students how, you know, what's inside this simple video game. Now, if you're not interested in that, and you know, and most of the people that use Visual Python, they're doing, like, if you look at the Matter and Interactions curriculum, almost none of those activities are activities where you're interacting with anything. You hit go and then you watch. You know, which is you know, probably a remnant of the way that computational physics is taught at more advanced levels. But we have to change it. I think that there's a golden opportunity with using these video games to get kids to think about what is actually happening in the real world as things evolve, instead of just sort of like watching it passively. I really think it's going to be more engaging, and I hope someday to prove that they can learn more from that approach than just sort of the, you know, hit play and watch approach, which tends to be what Visual Python is about.
Yeah, thank you. I mean, those are really good points to consider, and I mean, useful.
And I also argue that the whole thing with the spacing, like if you have the spacing wrong in a Python program, then it messes up the logic of the program. You know, like, I mean, I've had a problem myself in my own research codes. I put an extra space in something, all of a sudden the for loop doesn't work. And I lose an hour trying to figure out that all that happened was a space that I missed. So that I find to be very frustrating with Python, and something I would not wish upon my worst enemy, nor I would wish upon an absolute beginner coding student. Now, the Achilles heel of what I'm doing is that it's super easy to delete curly brackets. And so 9 times out of 10, the most difficult debugging thing happens when a student accidentally deletes a curly bracket, and you have to hunt it down. And the debugger is not always very good at figuring out if a curly bracket has been deleted, because it assumes that you know what you're doing with the curly brackets, but if you screw up other things, it can catch those things. So I don't know. So I'm not going to fall on my sword about that one, but I have thought about these things in some depth.
There are idiosyncrasies to all these things. I've used both MATLAB and Python, and they use the semicolon differently, and I always screw up one or the other when I'm going from one to the other. So it's the same kind of problem. Other final.
Yeah, interestingly, JavaScript is very robust to semicolons. You can delete a lot of the semicolons; it'll still run.
Yeah,
it's almost too robust to semicolons.
Yeah.
Actually.
Any other questions for Chris? Well, Chris, I'd like to thank you so much for providing this webinar. And as I said, we will have a YouTube version of this. I'll send you the link so you can post it to your own site as well. And this will be up within the next couple of days. And so thank you again, and thank you all for attending. And we'll call it a day then for this webinar. And hope you'll tune in again when the next webinar comes around. So thanks for everybody for participating.
Yeah. Thanks, Dave. Thanks so much for the opportunity.
Thank you.